exciting. No, we're not live. We're actually not live. But today, the person speaking to us is Michael Mayer. He's talking to us about snake venom. But before I explain who he is, make you all super excited to hear from him, I have a couple announcements. So we have 305 either next week or the week after. I will figure out which week it is and send it out in an email. But 305, in case you don't know where that room is upstairs. So come in, enter through that door, and it's basically kitty corner upstairs. Kind of go down the long hallway and around the elevator to your right. It's one of those rooms that's sticking off the end of the building. You're walking here and you kind of see it floating there. We'll be there because there is a class. Is it next week?
2 weeks.
2 weeks. 2 weeks. Yeah, there's a class 2 weeks from now in this room. Some of you might be in that. It's the data carpentry software carpentry workshop. I am killing it today. Software carpentry workshop. And also, just an announcement, I will be stepping down from running the R group in the fall. I will still be here, but I'm hoping that someone else wants to pick up the Slack and I can train you run the R group. In addition to running it and like setting up meetings, you also can get research credit or independent study credit. That's how I've been getting through my advisor. So it could be useful, especially if you need some of those last credits towards your dissertation or your master's, whatever else you're doing. So let me know if you're interested in it. I will announce about it pretty much every week until we have somebody. So, at some point, sign up to save yourself. All right, so Michael is a PhD student with New Hampton in Syria, and he specializes in aquatic ecology and studying the impact of pharmaceuticals and other products of human use on plankton communities. That's why he's talking about snake venom today, because he also does a lot of multivariate stuff, and he will explain how that story came about, so to
Right, yeah.
And also show us some cool stuff on how to analyze this type of data. So, take it away.
Thanks. Cool. So hi, everybody. Full disclosure, as Ellie said, I'm not a venom person. I know nothing about venom, really. But yeah, I thought this was a pretty cool very cool idea for a research profile, and I think it's a way that, like, if you know enough about R and like some data analytics, you can kind of lend yourself to other people who may need your stats help. And that's really how this project came about. So before I start getting into like all the stats and all of the R code, let me just say how I want to how I think this can be set up. First, we're going to talk about how the project actually started. Then I'll tell you how I did what I did, and then we'll walk through a little bit of the R script. So I have notes for absolutely everything. I doubt I'm going to get through all of this. But on the WordPress site, there's an R markdown of absolutely everything from beginning to end. And all you should need to do is just copy and paste the code and then run it on your own RStudio.
Right. And I will also upload. Did we upload the data to that part too? It will be. The data will be on there. I also sent it out to you guys.
Side note, just so you know, as cats would say, the subset data that was sent out is actually a portion of what the R script runs on. I will show you I will highlight the differences between the subset of data that you received and how to run it fully with R script on the website. So, without further ado, let's get into talking about this project and venom data. So, a long time ago, in a state far, far away, like Ohio, my good friend Justin, who is a data collection wizard or beast, he collected, he went through about 500 different studies, and with an army of undergraduates, and they started and basically they were doing this systematic review of snake venom protein compositions and how that might potentially be related to antibiotic effectiveness of a snake venom, because they were teaming up with this microbiologist, and he's like, some of these venoms are really good at like destroying certain types of bacteria, and we've noticed that snakes tend to have a certain microbial community in their mouths. Maybe there's a relationship between the proteins and the efficacy of a certain venom. We should really do a review on this. And so they did. Simultaneously, Justin and his team of undergrads started putting together a data frame, something that looked like this. So please tell me if you can't read this. I'm really sorry, but I'll do what I can. So it started off like snake species. They had a column for snake species. And then they started collecting information on about 15 different proteins, so 1 to 15. And they were able to get these protein data as percentage of total protein composition. So that's the percentage that a given protein represents of the total proteome of a snake's venom. They also managed to get efficacy data, so whether or not a certain snake species was associated with antibiotic effectiveness. And they coded this as 0 or 1, whereas 0 is not effective, 1 is effective, okay? And then they also had some metadata where they had bacteria species, and then they also had some some metadata on those types of bacteria. So they had things like bacterial morphology, they had respiration, and they had gram stain of bacteria. So if you look at that CSV, I can probably plug in my computer to do that. That's pretty much the subset that you guys receive. So you should have a subset that is of just the snake species, some proteins. You should have 3 efficacy data, and then these bacteria should be different, but morphology, respiration, rates should all more or less be the same.
Do you want to see the data?
If you, yeah, sorry, I thought about it, and I'm like, no. And so I can talk more from this. So what my friend Justin said is, that's not it. So what my friend Justin said is, it'd be really great if we could come up with some relationship between these protein concentrations and this efficacy. And he's like, I just don't know how to do it. Because my friend Justin, like I said, is a beast at data collection, not always as strong with statistical analyses. And he's like, hey Mike, do you know of a way that we can do this and we can create a model that given a protein composition, we can accurately predict efficacy? And I was like, well, the way that I would approach this, and I'm going to pretend like everybody's at base 0 for statistics, so I'm really sorry if it sounds like I'm here. But the way that I thought about this was, it's kind of like this fancy thing called a discriminant analysis. And that's really too fancy of a word for me, so let me give you the statistics book definition of discriminant analysis. Is basically the extent to which we can separate 2 or more populations based off of some measured variables. Also, that's really, I just said it, I'm going to draw a picture because I understand things through picture, and hopefully this will clear up what exactly this analysis does. It's simpler than you think. So let's consider a univariate case, right? Say we've got some measurement of protein X, and we want to look at a frequency at which we observe protein X, right? And we already know that there's 2 populations, right? We have population 1 and population 2. And population 1, we're going to say that's the population of all snake venoms that are ineffective, right? And population 2 is the population of all snake venoms that are effective, okay? So that's coded as a 1. And what we can imagine is that for population 1, there's some type of distribution, right, of those given protein concentrations. So that's described protein 1. And then we can imagine that for population 2, there is also some distribution of protein concentrations. Population 2. Okay, everybody good so far? Okay, next one. Well, where are my markers? Okay. So, what we can say is that if a protein concentration falls in between this range, we can assign this to population 1. Okay, we know we can accurately predict that. We also know that if the protein falls within this range, we can say, oh, that snake venom belongs to population 2. It's probably effective. We run into a little bit of a bugaboo where, I should say, the cobra's out of the bag. That's good. Here's our cobra out of the bag. We got a charm. So, stopping that. Is in this crossover area, right? Because there's some of this area that we could easily confuse between population 1 and population 2. So it's possible that if we were to come up with some formula, right, based off of protein composition to assign to each population, our model could predict population, it should be in population 1 when it's really in population 2, and vice versa. Make sense? So the way that we can go about doing this is say, okay, we'll split it down the middle. And if you happen to fall in the left-hand side of this, doesn't matter, we're going to assign you to population 1. If you fall on the right-hand side of this, you're going to go to population 2, knowing that there's a chance that that very well may be from the wrong population. All good? So at the very end, we can create a sort of matrix, where if we were going to say what our model predicts, and our model can predict a 0 or a 1, or ineffective or effective, and then we also know what it is in reality, right? We know what these who actually belongs to which population. So in reality, we also have a 0 or a 1, and then we can compare these two. So if I predict it's ineffective, and it really is ineffective, we can say that that is our true negatives. Same thing, if I predict it's positive or effective, and it really is effective, we're going to call that our true positives. And then if I predict it as effective, it's really ineffective, that's a false positive. And then if I predict as ineffective and it's really effective, that's a false negative. Everybody good so far? Okay. So that was my approach. What we need to do effectively for this discriminant analysis is we already know what these are. We need to come up with a model that can best assign individuals to each of these populations and then compare our predictions to what they actually are. But then the question becomes, well, we have 3 different proteins, or at least in your subdata set, we have 3 different proteins, right? And you can think of multiple different combinations that you can make with those proteins. There's so many different models. So what I did is, and by the way, cite your sources. What I'm about to present is really nothing new. If you want to read someone's paper that really pioneered this, Steve Katz, Ali's advisor, has a paper from 2015 called the Melosira years that does this with plankton community for plankton algal blooms under the ice and using climate data to predict it. And when I read his paper, he and I talked, and he was great. And he's like, why don't you just do what I did here? And I'm like, oh, you're totally great. I can do that. So like I said, exhaustive model selection. What does that mean? So if we were to look at your data set, we can really take 4 columns, right? We can take the efficacy data, we can take that protein 1, protein 2, and protein 3, okay? And our goal is to create as many different forms of a predictive model as we can. So what we can do is we can take efficacy as a function of protein 1 plus protein 2 plus protein 3. We can say efficacy is a function of protein 1 plus protein 2. We can say efficacy is a function of protein 2 plus protein 3, et cetera, right? We could even have these be individual. Maybe it's just protein 1, just protein 2, just protein 3. Okay. Now from each of these models, we can get a value called AIC. And Reader's Digest version of what AIC is, the way that I say it, is a way to assess model goodness of fit, but penalize models that use a ton of parameters, and thus might be overfit to your data set. So a good AIC is something closer to 0. A worse AIC is something greater than 0. Fair enough? Reader's Digest version. So at the end, we have an AIC for each of these models, right? And we can make a plot. I'm sorry, this is lower than I intended it to be, but where if we were to index each of those models, we can have the AIC be on the y-axis. And what we would expect is that way out here at model number 500, whatever, maybe all of those parameters are really shitty at predicting efficacy. So we have a really high AIC. Same thing. Maybe it gets a little better. And then in the middle, we get a few models that are more or less equivalent. But then, as we move toward it, but then there's going to be a few models where a very small change in model index imparts a big change in AIC. And these are the models that we're going to focus on, because at least compared to all the other combinations we can make, they do much better. Does all that make sense? Okay, so let's code that up. Sorry for going into detail, but I know if I didn't explain that, this is not going to make sense. So yeah, if you want to pull up the data, and then I just opened up a little R script, and if you just want to bring that into R somehow, you're more than welcome to put it along. Let me get mine. So, oh, thank you. Sorry about that. Okay, so what I'm going to do, is everybody ready? Is everybody, if you're going to code along, great. If you're not going to code along, that's great too. Consult the markdown document. So I'm going to bring in my library. And now, yes, this is as easy as you can. So I'm going to name my object just for my models. Oops. And then I'm going to use the function glMulti. And then I'm going to have my response variable, effectiveness. And I'm going to say that is a function of, no, I'm going to misspell these, so I'm just going to copy and paste them. Phospholipase 2, A2, plus metalloproteinases, plus this Whopperin Phoenix BPTI, whatever that is. I did these analyses, I don't know. The data is going to come from this ELAP. And by the way, if you're wondering what this object name means, this is just the format that I use when I was subsetting the data. So it's all of the Elapidae snakes tested for their antibiotic efficacy against gram-negative facultative anaerobic bacillus bacteria. So there's that. Now, this is where it gets a little different from your regular GLM, right? So what I'm going to say is level equals 2. And what that means, let me make a comment. What that's going to mean is interactions are considered. Meaning that I can look at interactions between two proteins. So it's going to go through, so for that, let's say it's protein 1 plus protein 2, it's going to add a third term, protein 1 interacting with protein 2. And it's going to iterate through all of those. The thing with glMulti, if you're using it, it only considers up to 2 protein interactions. So 3-way, 4-way, whatever, are not considered. Okay, next method is going to be H. That means that's going to be an exhaustive method. There are other ways of going about how to create these different models. I'm not going to go into those. And then our criterion is going to be AIC. You can also use EIC if you're in the Bayesian world. Yeah. AIC. Our convet size is going to be 100, and that just means that in this object that we're creating, the elopgram-neg fact-bacillus.model, only keep the 100 best models. I'm not going to count that. And then we're going to do plotting, which just means or do I want to make a plot of all these things as I iterate through these models, and report equals true, which is going to tell me what the best performing model is, what the critical AIC value is, and what the average AIC value is. Okay, now fit function, we want this to be a GLM, and we want our family of functions to be a binomial. Basically, because this is logistic regression, we have a binary response for a continuous predictor. And fingers crossed,
Really quick note, if you're using GLM multi, it's a super sweet package. In my experience, it doesn't handle very well if you've got more than about 8 response variables.
Oh, no.
So, which is a lot, but I'm just saying sometimes you have 8.
Unless if you're not considering interactions.
Right, you have to not consider interaction. It will freak out on you. Even throwing it to a computer with a bigger memory doesn't solve the problem. You really shouldn't be shotgunning it anyway, but if you were, for some reason, decided to do that, this is not the right package for you.
And what you have 3 proteins. I went through I'm gonna like pat myself on the back. There was a fair amount of cleaning and variable selection that went into taking those 15 to 3. Largely what I did was, if you look at the R Markdown script, don't be intimidated when I have variance, it's mean, variance, and variance to mean ratio. Basically what I did, I came up with these criteria where if a protein concentration doesn't really vary that much from snake to snake, it's probably a really bad predictor. Even if it's constant, because let's think about it, like if it's constantly 12% of snake venom throughout all snakes, there's really no difference if it's effective or ineffective. That's what makes this, and my collaborators, this is something that was a learning experience for me. My collaborators are like, whoa, but that one protein that you're excluding, our hypotheses say that should be a really important protein. And I was like, yeah, but that protein is relatively the same throughout all snakes. It might be really important for efficacy, but in terms of predicting efficacy, it does a really bad job. Cool. And then I also looked at correlations between proteins to avoid redundancies where 2 proteins correlate with concentration. One almost came out. So, I think that's good. Let's plot this. Okay. And that's it. So, we get our final index criteria profile, which is pretty much like what I drew up there, right? We get few really good performing proteins. This red line, the standard for AIC is basically you take your lowest, or with model selection, is that you take your lowest AIC value, add 2, and then you would say that, okay, well, everything within this 2 AIC window is relatively the same with respect to AIC. Yeah, and it follows the way that we kind of expected. We have a few models up in the top right that do really poorly. We have a few models where, it's not, the difference between model 19 and 20 really isn't that big of a change in AIC, but then when we get out to here, we see a fairly precipitous drop-off, where it's a very small change in model index results in a large change in AIC, and that's what we want. Okay, I'll be real, that was like my bare minimum of what I wanted to get through. So if I have more, if we want to continue. But I wanted to ask if people have questions.
Or comments.
Or comments. You can, and by the way, you can totally say, Michael, the way you did this is wrong. Yeah.
This is super interesting that you do. But I had a problem doing the Java stuff, and I still haven't figured it out. I know you mentioned some troubleshooting in the email, but could you just clarify the troubleshooting with Java issues?
Yeah.
So this is the problem that I had. I'm not saying that my problem was the same as your problem. I had an outdated version of Java on my computer.
Yeah, I just updated it and I submitted
64-bit mode?
I don't know how to do the 64-bit mode, honestly.
It should be an option when you're downloading.
Yeah.
So you either download a 64 or 32. And it needs to match.
And it says package R Java could not be loaded.
So the Java on your computer, you download Java from the internet,
just
not our Java, but like Java.
Yeah.
Okay. That's where there's normally the option of 64 or 32.
Yeah, I don't know if it's the browser I'm using or what, I didn't see an option. So maybe I'll just parse it.
We'll see if you'll do exactly yours, and I'll come over here and we'll see if.
It's really frustrating.
I would just like to be able to use this,
Yeah,
and
okay.
if I can.
And it doesn't happen to everybody on every computer, so. What?
Did anybody else have any other questions besides Java and R not playing well together?
First did this, but instead now
Yeah. Yes, you need that. For some reason, try that. That might help.
Should it by
Yeah. And then you'll have to reinstall.
Yeah.
Did yours go? Or?
So after you update, you need to reinstall it?
If it doesn't work,
Okay.
try it. You can try just uploading the library, but doing it from scratch, especially if it's going to old directories.
That's true. If everyone can get GLM multi running by the end of this, it will be a successful gathering.
I'm gonna call that a success.
Yeah.
That is a success.
It's really useful if you're doing model selection. The
Yeah.
first time I did it, I wrote them all up by hand.
So is the most useful part of this basically that interactions thing where you don't have to specify them? Or is there something that's more useful about this package?
The GLM package?
Yeah, the GLM multi. Like, how does it differ from other GLM?
So it automatically, there are other ones too, but it automatically creates your combinations. So you'll see in the plot has a whole bunch of models. If it just did the 3 he put in there with the negative interaction term, that'll only be 1 model with 4 predictors. But at GLM multi goes through and it goes, okay, you have 3 predictors, A, B, C. I'm going to make a model that's response in A, response in B, response in C, response in A and B.
It's kind of like, can you do step up or step down with another
Yes.
function? It's like that, but it's doing it.
It does it all at once, which is why it's such a memory hog and hates multiple variables, because it does it all at once.
Yes.
Does the output like provide you the hierarchy of that stores based on
That's exactly this. So it already orders them. So what I did, these are, I forget what these objects are, S4 objects or something like that.
Its own
It's
syntax.
its own type of object, so you have to use the @ sign. And then if you just do formulas 1 to 5, it outputs like right here, the top 5 best performing models. Cool. Yeah, I can also talk about one more step, I think. Because this is as much as I would love to say that you do this, you found your best model, you're done. There's a lot more. Like I said, the Markdown document goes through it in more description. But yeah, why not? Why not? You're here. You track through the snow. You get your bang for your buck. Okay. So trying to do yeah, let's do it. So okay. So like I said, when we found the AIC, this is the best model in comparison to all of these other models. We don't actually know that this model describes our data well. So we should probably figure that out. And the way that I did that is 2 different ways. Number 1, you can use R². Because these are logistic regressions, it's a little funky, so we call it pseudo R².
For deviant squares.
Deviant, yeah, exactly. In my Markdown, I have called pseudo R².
Well, they're different measures, but you'll find
Yes.
people use deviant squared or pseudo R squared. It's the same thing. It's just a different nomenclature.
Survive a second, you should Sorry, my cat is coming back. And then what I also did was something called, because it's just 2 binary, we can do something called a receiver operator characteristic, and then from that calculate a metric called AUC. Okay, crash course, Michael's Reader's Digest of what an ROC is. Is anybody? Yeah. ROCs. So if let me erase this. So that people in the back can see. If I just erase that confusion matrix. Okay. So we had the false positive rate, false negative rate, true positive rate, true negative rate, maybe in that order. If I were to plot the false positive rate against the true positive rate, okay? And let's just say we have perfect discrimination, meaning that our true positive rate, independent of the false positive rate, remains 1, right? So this goes from 0 to 1. This goes from 0 to 1. So we're straight up to 1, even if our false positive is 0, and our true positive remains 1 throughout the entire duration, independent of false positive, right? We can say, what's the area under this curve? It's 1. Okay, now let's say okay, what if our false positive rate increases 1-to-1 with our true positive rate? Meaning true positive rate equals false positive rate. Can't really, it's exactly the same thing, so we do a really bad job discriminating between the true positives and the false positives. That goes at a 1-to-1 line, meaning the area under this curve is 0.5. So if we want a good performing model, we would want some curve that is just better than 0.5. Make sense? So what we have are these two alternative metrics of assessing model performance. So let's code that up. I think I'm going to go over here to my markdown. Should be exactly the same. Okay. So there's really, even though this might look intimidating to some people, it's really, I think, I'm not about efficiency. I'm just about doing it the way that I can do it. I've always said my greatest efficiency is being inefficient. So hopefully you can at least follow along. So what I'm going to do is create some empty vectors to put my model, my AIC, and my AUC, and my R squared. And all I'm going to do is I'm going to add this for loop that iterates through each of those stored models in that model variable that I originally created from GL and multi. By the way, all of this code is on the markdown document, so you don't need to keep pace with me. It's all online. And it's going to iterate through and calculate R squared and AUC for each of those models that the GL and multi produced. And then what I'm going to do is just create that, put that into one data frame. And what?
Hold on for a second. So if you're not following, if you've never done AUC or ROC, what it's doing is it's predicting, it's using the model, it's then predicting what it thinks the values are, and then comparing that value to the real value, right? So if you ever use the predict function in R off of your model, no, it's okay. That's what it's doing. If you also, you can see it in there with the predict statement, it's in the middle of the for loop. So he's basically looping through an object, he's making a for loop so it does it automatically, he doesn't have to tell it which models to use, and then predicting off of each model, and then calculating what that false positive, false negative rate is, and then calculating the AUC. So he's doing it all in one step, but each step is coded inside of this formula. So if you break out the code when you're reading it, some of those may be familiar to you. Yeah.
So if we were to look, sorry, the models are so long they get pushed down, but these are the model indices as well. What we see is that our best performing AIC model, excuse me, is probably not our best model to describe the data. Because even though it has the best AIC, so 2 plus 40, we'll call that 45, so up to 47 AIC points, we'll say. Those are the models that we should be looking at. If we look at model 2, yeah, the AIC is worse than model 1, but the R squared is better than model 1, and our AUC is also better than model 1. So what I'm going to say is model 2 is actually our best performing model when it comes to describing the data. And so that's what I'm going to dub our best model. So all analyses after that, I'm going to use with model 2. That's my second stop point for where I wanted to get to. I have one more thing. I did not expect to get this far, but are there any questions?
What was your highest R squared?
I don't know. The 0.425.
Okay.
Is the highest R squared. Yeah. And all the AUCs go down from 0.87.
What is it?
Ooh, that
Yeah, it was
Sorry,
a
I should
model.
have that.
Yeah. Yeah, and if you haven't done AIC before, AIC does take into account long performance, but it penalizes models for being more complicated, right? So it's not surprising that you have high values, but this is part of the reason you can't use AIC to really know what your best model is, because sometimes your goals aren't to have the most parsimonious model, which is what AIC's goals are.
And
yeah.
when hopefully all of this is published, you can see that for certain sets of data, the random model was actually the best performing model by AIC, but that's only because like the most complex model maybe has the second best AIC and has like an R squared of 0.9. So I'm like, okay, no wonder. Yeah, it's because there's so many parameters that the AIC got bumped down or up. Any questions? Oh, I guess one thing that I can't, yeah, let me show the others. Oh, let's do this real quick. So what I started doing was I'm like, okay, let's put back in our model 2 and actually calculate that confusion matrix that I showed. So the true positives, true negatives, all that stuff. So this is just using that model to predict, like Ali said, saying, okay, go and predict which population you think these snake venoms should go into. Okay, we got our ROC curve for the best performing model, looks pretty good. And then this is a little thing that creates that, hopefully you can see this, that confusion matrix, where here are our predicteds. So 13 of our 19 negatives were predicted as negative, and 20 of our 24 positives were predicted as positive. So I think that gets to an accuracy. Accuracy just means true positives and true negatives over the total number of samples. It's got an accuracy of like 76%. Whether or not that's good, I don't know, but I think I'm proud of that. And then what I also did, so if we
Did you run through and create confusion matrices for any of the other models?
no, I didn't. Oh, actually, you know what? No, I did something else. What I did was I permuted the variables and calculated the accuracy for a best performing model. I didn't do confusion matrices for the other model.
I'm just curious how different the different models would make
That's
sense
true.
in the confusion matrix.
Yeah, I don't know.
Not strictly necessary. Just curious.
Right. That's really good. I like that. Yeah. Pause. Where are we going? Oh, so something that I did do is, from a biological standpoint, I was wondering, well, what about these misclassified snakes? What about them makes them unique? And so what I did was, because I have effectiveness and the prediction, I can say, okay, well, let's filter those out. And I can look at my false positives, and I'm sorry, off the top of my head, I don't remember what about these false positives makes them false positive. I have to go through by hand for what the summary stats were. But yeah, this is a nice way, from at least a biological standpoint, to be like, okay, if I'm bringing in my new snake venom and I throw it in, and it's showing it's positive, but I know it's possible to get a false positive, what about the false positives make them show up false positive? And that's a really handy way that you can go about that. And then we have this last point. If there's no questions, I can blitz through it. And by blitz, it's actually something that you can blitz through. I'm not gonna like sprint on it. Everyone good? Okay, so it'd be really nice if we could assign a p-value to this model, because people like p-values. And to show that this model truly is significant. So, if you give a hoot about p-values, I say permute. So that was way funnier in my head. And actually, I can probably, okay. So
All your
permutation,
puns are going to be on YouTube.
right? Oh my god. Adam Griffin and I will just be like, sorry, we've been talking about Adam Griffin like for the past week. No, like this week. Anyway, so basically what permutation means is just randomly mixing up your data and then reevaluating. That's how I define it. And all we're going to do is that if I have, whatever. That's efficacy, this is protein 1, protein 2, protein 3, and say this is my efficacy data, and I have protein concentrations assigned to this, or assigned to each of these efficacy data points. All it means is keep these stationary, randomly mix these up. Because basically what we're saying is that our good performing model, our best performing model, is not random. It's not a product of randomness. So the way we create randomness is just mix these up and make them random. And then what we'll do is we'll plug that newly fitted model. So we'll mix these up, fit the model again, calculate AUC, and then put that in a vector, Mix these up again, do that 1,000 times, so we'll have 1,000 different AUCs for shuffled data. And then what we'll end up with, if you can imagine, if we were going to make a histogram of AUCs and the frequency at which you see these AUCs, we could get a nice little distribution. And then we plug in our AUC value that we initially got with our not mixed up data. And we say, okay, how many AUCs are greater than or equal to the AUC that we observed? And the probability of seeing a value greater than or equal to the value you observed is a p-value. So let's code this up. And for some reason, like, I don't know why, I really enjoy coding permutation stuff. I don't know why.
Can you code mine for me?
I find it fun. And it's probably really, like, weird or whatever. So all this is doing is the exact same thing that the other codes have been doing. It just permutes the effectiveness data. Takes a second to run through, and it's going to do this 1,000 times. It's going to mix up the data 1,000 times and recalculate AUC. And we're going to make a histogram of that. So there's our really nice little histogram. And then we're going to plot our AUC. Right? So that's probably a product of me only doing this 1,000 times. Maybe, I don't know. Or maybe our data is just that good. It's just that good. But yeah, so there are no models that perform better than ours. So I'm going to give that a p-value of less than 0.001. And say, wow, we not only have what we think is the best performing model, but we also have a significant model that is 76% of the time accurate. And yeah, that's how I managed to use data.
You're using the markdown as a supplement.
Yes. So if you're interested and you'd like to do this on your own, this is the markdown that I can pull up. What is it?
It's our stats.
Our stats.
Yep.
WordPress.
There you go.
So this is the entire, this site. This is the entire document. Like I said, okay, so this is the one thing that I said I would point out that I didn't point out. This markdown document was built with a larger data set. So it works. When I said I pared down those 15 proteins to 3 proteins, I walked through how I actually did that, how I calculated mean variance, ratio of variance to mean. Sorry, these outputs got a little wonky.
Well, we'll upload the raw markdown that made this along with the data, and you can download both, and then when you open it in your own browser, it's not constrained by WordPress's weirdness.
The only thing to keep in mind, because the only thing to keep in mind is that you will be getting a subset of the data that only has 3 proteins. So if you're starting with that 3 protein data set, you're going to want to start here at the exhaustive model selection rather than up here, which has all 15 proteins.
But yeah, quick plug for the research profiles is since Michael has everything in a markdown document, it's going, when you submit, this is your supplemental, right?
Yeah.
Yeah.
Oh yeah.
This is going to be the supplement of the paper, which is already done and incorporates all the R code, which journals are increasingly requiring people to submit their code. So, already done it.
And in the case you forget everything, when you forget everything that I wrote up on those whiteboards, I also have a quick 3 paragraphs that walk through each section, why we're doing each section, what it is, and then I try to comment my code as best as I can and describe which section or what each chunk does.
Also good for your own project when you forget where you left off a month ago.
That is why I use Markdown. Because I hate reading comments in RScript. And I'm like, no. Cool.
Any other questions before we call it?
Cool. Thank you, everyone.